All right, notes today will be called tangents to circles. Or we'll say tangent lines to circles. And when we say tangent, we're not talking about the trig function tangent. We're going to define this a little bit differently. And so let me start off with some definitions. So two objects are tangent to each other if they only intersect at one point. And right now we're going to look at a line being tangent to a circle, but later on we'll look at circles being tangent to each other. I think that's all we're going to be looking at, but any other, you can have other objects that are tangent to each other as well. So a tangent line to a circle will intersect the circle at only one point, called the point of tangency. Okay, so let me give you a little picture to go with that. So if I have a circle and I pick a point on that circle, and I want a line to go through that point, but the line can't touch any other point on the circle except for that point. It's going to look something like that, right? And let me, okay, so put some points. So say this is A, B, and let's let the center of the circle be C. And so notation-wise, we'd say line AB is tangent to the circle C. So there's some things that are true about tangent lines and circles, and that we're gonna explore some of those today. So I'm gonna set this up again, very similar to what we just did. So if I have a tangent line, and let's say the point of tangency is at point B here, and center in this case is A, and I draw my radius to that tangent line, what do you think is going to be true? Yeah, they're going to be perpendicular. So the radius will be perpendicular to the tangent line at the point of tangency. And so that's really the idea we're going to work off of. And so there's two, it works both ways. The converse is also true. So we're going to write that down. So if AB, our radius, is perpendicular to our line, our tangent CB, well, we don't even say, so if it's perpendicular to a line, CB, and we don't know if it's tangent yet, but it's at some point B on the circle. then CB, in fact, is tangent to the circle. Okay, which is just saying, okay, so if these are perpendicular at point B, then there's no way that that line can cross through the circle at any other point. That's what we mean by tangent. That's the only place that can touch the circle. Because if you pick any other point on that line, right? Let's say point. Well, let's look at point C, right? Point C has to be further away from A than point B, right? Has to be. Just for the fact that in a right triangle, that's your hypotenuse, and the hypotenuse is always the longest side. And so if it's longer, then there's no way it's going to hit the circle because your radius is from A to B, and you're looking at something further than the radius, so it's got to be outside the circle. So you can think through that a little bit, but that's the idea. So if the radius is perpendicular to your tangent line, sorry, if the radius is perpendicular to a line at a point on the circle, then that line will be tangent, in fact. And it works the other way too. So if CB is tangent to circle A, so if we know that this line touches the circle once and only once, then in fact it will be perpendicular at the point of tangency to the radius. So then AB will be perpendicular to CB. Okay. So everything we're doing today is just off of that result, that tangent lines are perpendicular to your radius. And what is a tangent line? It only touches the circle at one point. So I have 3 examples to show you and work off of, okay? So the first one, circle, center A. Pick B as a point of tangency. So we'll say that, and pick a point C on there. So we'll say CB is tangent circle A. I'll tell you, so if I draw from A to C, I'm going to intersect the circle at point D. I'll tell you that DC is equal to 2, and I'll tell you the distance from B to C is 7, and I'd like you to find the radius of the circle. Or tell me what the radius of that circle is. So let's kind of work through this one together. So let's put what we know, or what's given to us. So the distance from D to C is 1. Sorry, I don't know where I got the 1. 2. The distance from C to B is 7. What else can we do with this picture? Any ideas? Maybe draw something? Yeah. Okay, so how? What do I connect? Okay, if I draw A to B, that's a triangle. How do you know it's a right triangle? Perpendicular. How do we know it's perpendicular? Because of what we just said. That's tangent lines are perpendicular to the radius. Okay, good. So we got a right triangle, and right triangles can be so helpful in this unit, and we made one. Okay. So now what? Anything else we could put on this picture? What are we after? The radius. So maybe let's call that x. Okay. If we're working with side lengths, it'd be nice to use Pythagorean theorem if we can with the with this. But how would we write Pythagorean theorem with this? What would we write? X squared plus 7 squared equals, this is also x, right? So the full length here is going to be x plus 2, so x plus 2 squared. There we go. Go ahead and solve for x. What are you guys getting? We're still working. Keep working though. This one actually is going to work out nicer than the other problems we've been doing. The x squared should cancel out for you as you're solving. You're going to get a linear problem. It'll be a lot easier to solve. There's no factoring involved. Did you get an answer? You got 45? Close. 45 over 4 is what we want. So here's the work. Here's the work. Okay, so 7 squared is 49. X squared is x squared. X plus 2 squared is x plus 2 times x plus 2, and you got to distribute that. So x squared plus 2x plus 2x plus 4, you got to multiply all that out. And notice you got an x squared on each side, so you can subtract out that x squared from both sides. You left with 49 equals 4x plus 4. I'm just reminding us that we have some kind of distance here. So here you subtract 4, divide by 4, and you got 45 over 4, whatever the units are in terms of length. Okay with that? So this was built off of creating a right triangle, and the reason we were able to create a right triangle is because we were able to get that 90-degree angle because of the tangent line. And also we had to use the radius, idea of radius. It always stays the same, and we used x on both of those, so it made that problem work well for us. Okay. So next, let's draw a circle with 2 tangent lines that will meet at a point here. It's a what? It's not a central angle. Why do we know it's not a central angle? Because the vertex is not at the, at what? It's not at the what? Center of the circle. Now here's the center of the circle. Now I'll draw you a central angle, okay? There's your central angle. So let's call it angle A, B, C, and D. Okay. So if you have 2 lines that are tangent to that circle, and we have 2 points of tangency, at B and D. And if we were to draw the from the center of the circle to the points of tangency, the radius on each case, and split it down the middle here, we get two triangles. What do you think is going to be true about those triangles? Might be congruent, right? Let's try to show that they're congruent, and they are. Why would those two triangles be congruent? What might we want to add to our picture here? Okay, so for one, we got points of tangency, and the radius is always perpendicular to your tangent line. Okay, so we got 90-degree angles. What else is important? Yeah? These are both radii, right? So good. We're looking now. Now it's almost there. Yep. They share the hypotenuse, and so then, which one will we use? Hypotenuse leg, right? Hypotenuse leg by hypotenuse leg. These two triangles are congruent. Now, so we get congruent triangles. And so that's going to be important. So because we have congruent triangles, we can say some other things about this. We can say like the distance from C to B is the same as the distance from C to D, right? So CB would be equal to CD. We could say also that this angle right in here is congruent to this angle right in here, and so on. So let's try an example out. Number 2. Let me give you the scenario here. And I'm going to tell you that this angle here is, let's put the point here. Let's make this E here. Okay, so let's say this angle here is 40 degrees. So the measure of angle ECD is 40 degrees. And I'd like you to find the measure of arc BE. We're dealing with tangent lines. I didn't write that, but we got A is the center of the circle. BC is tangent to the circle at point B, and CD is also tangent to the circle at point D. We're going to assume all that in this picture. And what do we get? 50 degrees. Okay. Why? I'm going to draw this, right? Are you guys using the fact that we got two congruent triangles? And also that these are 90 degrees? Right? Just like we saw up there. So where do you go to get 50? So this right here is going to also be 40 because the two triangles are congruent. And that's got to be 50 because it's got to add up to 180. Central angles are congruent to the arc measure, so the arc measure is also 50. And we got it. Nice. Right? So that's kind of how that would apply to a problem. Told you I got 3 problems for you, so one last problem here. So this time I'm going to draw a few tangents to the circle. So here's one tangent. I'll draw 4 of them. Another one. Not perfect, but you get the gist here, right? So we got 4 points of tangency at A, B, C, and D. And then we have vertices at E, F, G, and H. And another way to describe this picture is the circle is inscribed inside of a quadrilateral, right? That's what's happening here. We've got a circle inscribed in a quadrilateral. So based on what you learned in number 2 and before number 2, you make any statements about the lengths of segments here? Maybe I'll help you here. Let me tell you that EH is going to be 10 units long. FG is going to be 15 units long. Let's say that HD is 3 units long, and DG will be 5 units long. And can you find the perimeter of my quadrilateral EFGH? Well, the problem is, like, we almost can, but we just are missing a side, right? We have no idea how long it is from E to F. If we did, we can find the perimeter. But we can use what we know about tangents to find that side. How? Okay, go back up here. In this picture, CB is equal to CD. You have this picture all around this circle here. So what's equal to what in this picture? Yeah. B, okay. BF is equal to FC. We don't know either of those, but that's true. What else is equal to what? Yeah. EA is equal to EB. We don't know either of those, but this is going to be helpful. Yes, what else do we know? This is equal to this, and that we know. So this is 3, and now it's starting to unlock things here. This is 3, this is 3. The whole thing is 10, so what's EA? 7, right? Because it's got to add up to 10, right? 7 plus 3 is 10. And so that's 7, so this has got to be 7. We're almost there. These are both going to be 5. So FC, although it doesn't look like it, is what? 10. And so this is 10. And now we've kind of unlocked the whole figure. And now we can find the perimeter. So my perimeter is going to be 10 plus 15 plus 15 plus 17. Which is what, 57? Oh, I'm sorry, I messed up. Should be an 8, not a 15. So let's try that again. So we got 40, 50. All right, last mistake here. All right, 50 units, right? You're thinking right? Yeah. Okay, and that's the last problem. So homework just deals with these ideas. Also mixed into the homework is prior ideas as well. So you got inscribed angles that I'll throw at you and all the other stuff just to keep you thinking and keep you remembering what we've had. You'll have factoring, all that good stuff as well. But we're going to stop our notes there.